Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll. As a working scientist, one of the things that I've had to do over the years is apply for grant money. And for theoretical physicists, this is a funny thing because you're supposed to say not only what you're interested in, the topic you're going to be working on, but what achievements you will have, what progress you will make. This is very difficult to do as a theoretical physicist. You don't know what's going to happen before you do it. As an experimenter, you can at least say what experiment you will build and when you will turn it on, what you hope to see. But of course, experimenters also don't know exactly what they're going to see. This is not only for theoretical physicists. There are kinds of experiments or observations where you can say what you're going to do, but the outcome is so unpredictable that it's actually kind of hard to wrap your brain around what would happen under different circumstances. One of those examples is the search for extraterrestrial life. I'm one who believes that it is plausible that we will find life elsewhere in the universe, and also we are not ready for that. Science fiction authors have thought about the discovery of alien life for a long time, mostly, I have to say, mostly in unrealistic ways. And I don't blame them. You know, they want to tell good stories. So they very often have structures of intelligence and technology and civilizations amongst the aliens that might be a little bit higher or a little bit lower than ours, but are at least recognizable, right? A galactic empire. As soon as you say the words galactic empire, you kind of know what you have in mind. It's not a coincidence that Star Wars is basically a Western or basically some kind of samurai film, right? Now, there's more sophisticated science fiction than Star Wars, but still, it's just hard as human beings to wrap our brains around the idea of what would an alien civilization be like that is 1 billion years more advanced than we are. And that's very possible that that's what we find, either 1 billion years more advanced or 1 billion years less advanced in terms of evolutionary timescale, in which case it's little tiny organisms that we can't really have a conversation with. And I don't really think that we as a species have thought this through because it's easy to dismiss it as kind of science fiction-y, right? Science fiction authors have talked about looking for and finding alien life for a long time, so we associate it with science fiction, not with serious science. This is a point made by today's guest, Adam Frank. Adam is an astrophysicist at the University of Rochester. He has a new book out called simply The Little Book of Aliens. And he explains in the podcast how not too long ago, the entire field of astrobiology was just considered fringey. It was just considered too speculative. You couldn't get any money to do it, etc. And this is even if you just thought about how do we do the chemistry and the geology and the so forth to allow life to exist on other environments. What you would think, I hope now, is a very straightforward scientific question that we've already talked about on the podcast. But there is also the possibility that we find not only unicellular life somewhere out there in the universe, but intelligent life. And it's hard to remove the connotations or associations with UFO conspiracy theorists and things like that. But we should, because it's an important thing that could actually happen to us. Of course, maybe it won't. There's the famous Fermi Paradox that says there should have been aliens that we could easily detect already, but there hasn't been. So it's very possible that there just aren't any technologically advanced civilizations out there in the world, but we should keep an open mind about this. I think it's also very plausible that there will be. So that's what we're talking about in today's podcast. We're going to talk about what kinds of aliens there could be, how you would go look for them, trying to separate the seriousness from the less serious ways of talking about this. And best of all, we will let you in on how real working scientists think about UFOs and associated controversies. So with that, let's go. Adam Frank, welcome to the Mindscape podcast.
Sean, it's great to be here.
So you've written a book about aliens, a little book because I guess we haven't discovered them yet. I'm hoping that after we discover them, the big book will be forthcoming.
Well, the book was little because what I really wanted was I wanted to write a book that was accessible as possible to as broad an audience as possible. There's some obvious reasons, so lots of people will buy it. But more than that, right now, the question of life in the universe is one that gets so much attention, both because of the scientific advances, but more because of what the hype that sort of goes around with UFOs and UAPs. Yeah. And I wanted people to have a fun, fast entry into everything that's happening, both in that subject, I took on that subject, but more importantly, what's happening with things like the James Webb Space Telescope, what's happening at the frontiers of astrobiology, because that's really the exciting part. We may be the last generation that doesn't know the answer to the question, are we alone?
Yeah, I mean, that's the nice thing about the subject, right, is that you're talking about real science. Maybe it's not the nice thing, but a thing is that there's real science as well as a little bit of sensationalism, and we'll get into that. But
right.
Let me just start by orienting ourselves here. Like, what kind of aliens are we talking about here? Not in the UFO sense, but there are extraterrestrial life forms. There could be extraterrestrial life forms that are just single-celled organisms. There could be ones that are at least comparable to our technological level, or there could be ones that are post-human in some sense and almost unimaginable to us, right? Like, do you personally have a target in mind when you think about aliens?
All of them. I think all of them should be considered as part of the search. Because the amazing thing now is we have the capacity to find all of them, right? When we talk about aliens, exactly, there's this sense of like, oh, unless it's an alien civilization, no one's interested, right? If we found evidence of a microbial biosphere, it wouldn't be interesting. And I reject that entirely. I think for, deep philosophical, historical, and scientific reasons, the discovery of any kind of life anywhere would be, other than Earth, would be the greatest scientific discovery in the history of humanity. So the important thing is we have the capacity to find biospheres, which is the signatures of just microbial or forests or things that don't build civilizations. We have the capacity now through technosignatures to find technospheres, evidence of a technology, of civilizations producing technology. And then, when we get to the truly high scales, those things should also be, that's a little bit more in the realm of traditional SETI. But we have the capacity to find those as well. So I think what really people need to understand is we didn't have these capacities like even 10 years ago. And now suddenly the telescopes and the detectors have gotten to the point to be able to find these bio and techno signatures. And NASA's all in. The whole scientific community is all in, which was not true again, even 10, 20, 30 years ago.
So, sorry, say more about that transition, about being all in that wasn't there 10 or 20 years ago.
Well, I have a whole section in the book, chapter in the book about the giggle factor, as we call it. We in the business call it. Because even when I was a graduate student, way back in the late 80s and early 90s, right? SETI, there was only SETI, right? Their astrobiology was not a thing. Right. The Viking landers had pretty much kind of closed the door on life on Mars because of those experiments that were done. And there was only SETI, and SETI was still kind of marginal. It was very marginalized, right? We had one professor at the University of Washington, where I was a Ph.D. student, who was into it, Woody Sullivan. And he was the only one. And, everybody loved Woody. But there was just this general sense, because he was a great scientist, he was a radio scientist. But there was always this sort of sense of, that's marginalized, right? That's something that's not, certainly don't do that for your career, right? Don't make SETI a choice. And that, I think, held for quite a while. And then after 1995, we get the first discovery of exoplanets. We get that Martian meteorite, which looked like it might have had evidence for life, didn't. But that launched like the new era of astrobiology. And starting from that point, NASA starts putting money into astrobiology. By the first decade of the new century, there are astrobiology centers. By the time you get to the 10 years ago, we now have a full census of exoplanets. We now know that every planet in the sky has a family of worlds orbiting it. Every fifth star, what I meant to say was every star in the night sky has a family of planets. And every fifth star has a planet in the habitable zone, in the right place for life to form. So, and most importantly, as I'm sure we'll talk more about, this process of atmospheric characterization, where we figured out a way to look into the atmospheres of these worlds that are 40 light years away and detect their composition, and therefore be able to find signatures of microbial life, or signatures of a biosphere, or signatures of a technosphere. That propelled everything. That changed everything. And now, last year, the astronomy, or 2 years ago, the Astronomy Decadal Survey was announced, where all of astronomers got together and decided what the next big project should be. And it's there in the name. The next big telescope is going to be the Habitable Worlds Observatory. So, the giggle factor is over. There's still some issues about technosignatures versus biosignatures. That's very much my thing right now. But even that is, we find we're overcoming that. So the scientific community is all in on the search for cosmic life.
There's a weird analogy to the foundations of quantum mechanics, in that in both cases, it was something people talked about for decades. There were giggles about it. It was kind of fringy. But then what is changing is that technology is forcing us to confront some things, and suddenly, now you're allowed to talk about it.
Yeah, I think that's a great analogy, right? Because it was quantum information science, and the idea that, quantum computers, where you have to swallow the superpositions whole, that suddenly people were like, what's a superposition again? And so I think that's a really nice analogy. It was the technology, the ability to first detect exoplanets. That was a major revolution. And then now, once we got really good with the transit method, which is where you find exoplanets by watching the star or the planet pass between you and the star, and there's a few moments there, or maybe an hour, where the light passes through the planet's atmosphere, and you can look at the absorption spectra, all the fingerprints that come from chemicals in the atmosphere hitting the light. That's what did it. And so now suddenly, and we're still on the hairy edge, like JWST is just at the edge. We might, if we're lucky, be able to get a biosignature. I mean, that would be amazing. But it's going to be the next telescopes, the 30-meter class telescopes, and then the Habitable Worlds Observatory that's really going to put us in there.
My impression is that JWST wasn't actually conceptualized as something that was looking for habitability of exoplanets. It was kind of designed to look at distant galaxies, but then turns out to be good for it. So it's kind of not surprising that if you purpose build a telescope, it would be able to do a much better job.
Yeah, that's it. And so it is actually lucky that the JWST has the right bands, the spectral bands that it's looking for, that actually overlap with many of the regions we think these bio and technosignatures may live in. So, for example, there was just this really interesting discovery about a month ago, where this entirely new class of habitable planet, what we call a Hycean world, hydrogen ocean world, had its atmosphere characterized in a way that actually indicated, this is. So let me just explain. A Hycean world it's a sub-Neptune, so it's a planet that's maybe 8 times the mass of the Earth, pretty big. And normally you'd think that would look like Neptune or Uranus, which was a world that is maybe has a rocky core and then just slushes and ices and then hydrogen and helium. Not a good place for life. But they have figured out that there's this possibility of a world that has a pretty thick hydrogen atmosphere, and hydrogen's a very good greenhouse gas. So what you could have below it, if you have enough water, is a liquid ocean, a warm liquid ocean. So this is this hydrogen ocean world. And this is what's so exciting to me, at least, this is an entirely new class of habitable world, right? We always think, you need an Earth and it needs to be in the habitable zone, yada, yada. And this is an entirely crazily different kind of world. And the JWST was able to find methane in the atmosphere, characterize methane in the atmosphere at like the 5 sigma level, so very strong detection. And then also CO2, I think at like the 3.5 sigma level. So that really meant, and those levels were enough to say like, this is what we think if there's a liquid ocean down. Like those levels fit exactly what the models predicted. So there's an example of the JWST doing atmospheric characterization at a very high level, and getting us information, even if it didn't have an actual biosignature. There was a little indication of dimethyl sulfide, which is what plankton fart into the atmosphere. But that was nobody really believed that for sure.
Yeah,
even the authors were like, "Look, we're just saying we see a little wiggle there." But it was showing that JWST is there for getting at least certain kinds of exoplanet information that we need.
So I would get into the actual technological capabilities of us in detail later. But first, I do want to lay the groundwork about this, what we might be able to find, in the sense that, like we said, there's primitive life, there's human comparable life, and there's way, way beyond human. And I think that one thing that people don't seem to quite internalize in this discussion is the chances that any life we would find are at the human compatible level are almost nil, in my view, just because it's very easy for a planet to have been evolving for either 1 billion more years than us or 1 billion less years than us.
Yeah, and actually we David Kipping and I and Caleb Sharp did a paper a few years back where David did all the Bayesian kung fu to show that, we called it, I think, contact inequality. That basically, if you detect somebody, odds are they're older than you, for a whole bunch of reasons. And, and that was always one of the first places like, okay, I really got to understand Bayesian statistics. But it was a very nice paper, and the result was pretty clear that, as you say, it sort of confirms an intuition that odds are you're not going to find somebody at your level of technology. In order to if you're going to find them, they probably had to exist a long time. Like if they only exist 200 years, good luck, unless they're very copious, unless there's a lot of civilizations like that. So in general, you're going to find somebody much older than you. So yeah, and we've only had technosignatures. We've only been a technologically detectable civilization for 100 years maybe. So it's just unlikely that you're going to find someone at our level, which is what makes a lot of the UFO stuff kind of a little bit ridiculous,
right,
because this seems to be so close to our technologies.
Well, and if the civilizations don't just blow themselves up, which is certainly one of the options on the table, do we even have sensible notions of what they would be like, or is that kind of just hopeless to speculate about?
No, actually, we're working on a paper on this right now. The whole idea, in the book, I talk about this NASA grant we got. I'm the principal investigator on this. The first grant NASA has ever given for atmospheric technosignatures. I recount the history in the book because it's important of this. Because I said, because of the giggle factor, there was basically no funding especially from NASA. And NASA tried a couple times to fund, at a very low level, some SETI work, and somebody in Congress twice or 3 times stood up and said, we're not going to waste money on these finding little green men, and killed it. So NASA, is a government agency, and they learned we're not going here anymore. And so it was literally in the call for proposals in these astrobiology programs to no, we don't want SETI, no radio SETI. So when we finally managed to get this grant through, which was not radio SETI, but was using, things like the JWST to find atmospheric technosignatures, that was a big deal. And one of the things we said was we're going to look, we're going to make a library of possible technosignatures, but we're also going to try and push the field forward, right? And this has been a problem with SETI, is that most of it is in the gray literature, right? There's, conference proceedings. There's never been a continuous, coherent, ongoing back and forth between the literature and then the next thing you want to do, because there was never a coherent community. It was just brave souls doing it on their own. So one of the things, to get back to your question, one of the things we're doing right now is to try and systematize futures, right? We're actually taking methods from what's called future studies, which has been applied to climate change, and trying to apply these to technosignatures. What, if anything, can you say might be generic about the evolution of civilizations? And it's been an interesting project because you got to map out the spaces, right? You're never going to be able to predict futures. You're going to be able to predict the fans of trajectories, the Absolutely. Wide range of trajectories. And so I think if you focus on things like energy use, try and focus on the physical aspects, not the sociological aspects, then you can sort of map out questions like, do they have interstellar travel? Do they have faster than light travel? Do they have, and so you can at least begin to get a sense of what those parameters look like. And the nice thing, of course, because of the second law of thermodynamics is your friend, right? No matter what happens, I doubt the second law of thermodynamics is going to be overcome. So therefore, that is going to leave imprints on your planet and on your solar system. So I think that's using the second law of thermodynamics which is what the Dyson spheres are all about, is a good way of guiding your intuition about what these civilizations and what the imprints will leave.
Let's not imagine that everyone here knows what a Dyson sphere is or the second law of thermodynamics. So how do those things help us look for life elsewhere?
Yeah. Okay. So what is a civilization? It's really just a mechanism for harvesting energy and putting it to work. And, like human beings 300,000 years ago, basically every day, every human being had one human being's worth of power, right? There's horsepower and there's human beings. But as we progressed working together, we were slowly able to harvest more energy so that right now, I had to do this calculation once, each of us has the equivalent in our house, just our house alone, of about between 50 and 100 human beings at work for us, just from, the power coming through the outlet. So the very famous second law of thermodynamics tells us that if you want to use energy to do work, you're going to create waste of some version. It could be waste, it could be just heat, random motions of atoms, but you can generalize that to mean you're just going to create crap. There's going to be noise. There's going to be, there's just going to be a consequence of trying to harvest that energy and use it for work. So this is a great thing to think about for alien civilizations because civilizations are going to be harvesting energy. It's the very definition in the definition. So a long time ago, back in 1960, Freeman Dyson, very smart physicist, realized that one thing you can consider that might be universal in the trajectory of civilizations would be to harvest as much energy as possible from your solar system, and that means your star. You would try and surround the entire star with solar collectors, get all that energy, and do whatever you want to do with it, whatever you're interested in doing it. So the idea was to build a Dyson sphere, a sphere around the star that had solar collectors inside. Now, he knew immediately that was gravitationally unstable. So really, these days, we think about Dyson swarms, just these giant planet-sized machines that are solar panels that are orbiting the star. Now, the thing about that is if you do that, you're collecting energy. You're going to, by the action of collecting and harvesting that energy, you are going to create waste heat. You're going to warm up, basically. And you should be visible in the infrared. The whole thing should be glowing. This giant machine should be glowing in the infrared. And he proposed that in that paper, that first paper. He said, this is what you should look for. And people have been doing that. People have been, there's been a few studies, Jason Wright in particular, recently, looking for Dyson spheres. And you can extend this idea to almost anything. One of the things that we've proposed is that in a planet that has civilization, you would see in the chemical networks in the atmospheres, you'd see evidence of the non-equilibrium processes and their dissipation that are going on. And you would be able to look for that in the atmosphere as an indication that there was something going on in that planet that was beyond just not having any life or beyond having just a biosphere. There's a cascade upward in sense of how much dissipation happens because of your use of energy.
Okay, wait a minute. I want to get back to that, but first I need to harp on Dyson's thing because I don't believe it. I don't think it's right. I think it makes a pretty simple error. As long as you have a source of energy that is hotter than your environment, then there's useful work you can extract from it. So if you're at all a smart technological civilization, you should cascade the heat that you're emitting back out in the universe all the way down to the temperature of the microwave background. So I don't think that Dyson spheres should be visible at all.
So you want to have a cascade of machines, but each machine is going to have some level of dissipation I'm not sure that you can harvest all of the dissipated energy. I think at some point you're going to have, you're right.
With a billion years of practice, I could figure it out.
I think, it's interesting. I think I recall papers. I recall a paper, I think, that was discussing about these sort of cascades of machines. But ultimately, right, you can't harvest it all, right? Some of it is going to have to be dissipated.
Yeah, you have to harvest. You can't lower your temperature below that of your environment.
Right.
Which I think is 3 degrees Kelvin. Yeah. All right. So that was one thing. But now and I do want to get back to the super civilizations, but now I want to hear more about this analogous thing, which I take it to be with just the existence of life, not necessarily with technology. And I completely agree that, primitive life obeys the second law and is not even very optimized to turn its energy into waste heat. So what exactly is the signature that you're looking for?
the life. So everybody should take a deep breath, right? All that oxygen in the atmosphere is a consequence of this invention about 2.5 billion years ago of a new form of photosynthesis, right? Which was completely changed the planet, right? So photosynthesis was actually not a very efficient affair before this happened. It required there to be, it was extracting iron ions. That's what it used as you get in a photon, you'd move some, iron in the ocean around, some molecules around ions, and then you'd be able to make a sugar. Once photosynthesis, once life figured out, I can use water as the substrate, right? That changed everything because water's everywhere. Now you're done with your rate limiting step. And so you break apart water molecule, use the hydrogen as part of the molecular machinery to make the sugar, and you burp out the oxygen. So that was an enormous change in the planet's history, right? That the introduction of oxygen into the whole geosphere changed. And it eventually put the oxygen into the atmosphere, the 21% that we have now. And it's that continuous flux of oxygen into the atmosphere is a driver of non-equilibrium chemistry, right? I mean, if that oxygen went away for whatever reasons, very quickly, I don't know the exact time, but certainly within 1 million years or so, all the oxygen gets bound up with rocks again, and it's gone. You're back to the previous nitrogen, CO2 dominated. So it's both. So the presence of certain chemicals, the flux of those chemicals means that your atmospheric state is non-equilibrium. It's life that's driving it in there. And then even more to the point, this is some really fascinating work that's going on now. People like Sarah Walker and others, and Sarah Seeger, have been trying this idea of looking for agnostic biosignatures, things that don't have anything to do with what's happened on Earth. And one of the interesting ways to do this is looking at the network properties, right? That you see in the chemical network in the atmosphere, the network properties of who's reacting with whom in a system where life is pushing those chemicals into the atmosphere is going to look very different. And they've shown, there's a great paper by Kim et al. A few years ago, will look very different than a random network. And so by looking at, who's connected to who, the degreeness, the degree centrality, all of these network topology characteristics, you can really see differences between biology building the network and just random or just pure geophysics.
Yeah, actually, I'm very sympathetic to that because every time people talk about CO2 or methane or oxygen or whatever, I'm like, okay, maybe here on Earth there was a certain way that was made, but come on, these molecules are so simple that maybe there's a different chemical process going on we don't know about. But if you have like some very complex hydrocarbon, I just invented a new word, a carbohydrin. Hydrocarbons are things that life naturally makes, or even very, very complicated molecules at all. That sounds like a promising place to look, but maybe those are harder to look for? I don't know.
Well, they will require bigger telescopes that have longer, where we can, the whole point of a big telescope is it's a light bucket. The bigger your bucket, the more light you gather, the faster you can look for a spectral feature. So it is true but we're just starting down this road. So this idea of agnostic biosignatures is something that really only in the last 5-10 years people have really begun, and there's been funding for. And so network properties of one of them, looking at, again, this idea of dissipation, trying to calculate the how far away from how far are you from the equilibrium state of the atmosphere,
right.
And using that metric, the distance, as a measure of how much life, dumb life or smart life is pushing you away. But I really love what is interesting, and we're working on this as well, the whole idea of information architecture, right? Using information theoretic measures of how this is what assembly theory is about. That's one of the things why those guys were interested in assembly theory. But there's others of seeing like just how do you measure how complex this molecule is or atom is, and how much does that allow you to say, okay, this could only be produced by life, or this could only be produced by technology,
right? Which probably can only be produced by life.
Right, exactly. Yeah.
So speaking of which, let's finish up the advanced civilization business. there's an obvious problem lurking in the background here. We've gone 25 minutes into the podcast without mentioning it, but where are all of these advanced civilizations? Didn't Professor Fermi point out a paradox in this way of thinking?
Yes, the infamous Fermi Paradox. What I like about the Fermi Paradox is that it's the first, it was 1950, right? And so in the book, I sort of go through this history. The decade of the 50s is amazing because you start with Fermi, then you have the Miller-Urey experiment, which was this first experiment that showed it may not be that hard to get life started. And then you end with Drake doing his first SETI search. But the Fermi Paradox is the idea that, look, if the stars, if intelligent life is common, and if intelligent life can figures out how to travel at even a tenth of the speed of light, then basically the whole universe should be filled, or the whole galaxy should be filled with intelligent life. They should have been able to hop from one star system to the next and settled and built up, civilization and moved on to the next. So that is what we call the direct Fermi paradox. Why aren't they here now? So, of course, if you're into UFOs, the answer is clear. They are here now.
There you go.
But if you're not into UFOs, there is an entire sort of, cottage industry of people coming up with answers to that. Well, we're a zoo, we're being held, they're not contacting us because they want to leave us alone and watch us. But I actually think, and we did a whole series of papers on this, I think there's an easier answer to this, which is the debate about the Fermi paradox was how fast does that civilization front move, right? Does it take, in the original calculation that Hart did of the Fermi paradox, 1975, Hart showed it takes about 600,000 years if you're moving at 0.1 C, which is very short compared to the age of the galaxy, hence the Fermi paradox. And then Sagan and others said, oh, no, it's going to stall out because of resource issues. We did a simulation. We made a little galaxy turning around, and we did, a really nice simulation of Jonathan Carroll, my former postdoc, ran this. And what we found is, yes, the front travels very fast. It's, you colonize your galaxy very quickly. But if you add the fact that civilizations don't last forever, right? I mean, civilizations die. If you allow the civilizations to die, now you have to ask, what is the steady state occupation of the galaxy? And what you find is you can end up with, depending on the parameters of your space travel, you can end up with pockets that are uncolonized or settled for millions of years. And those pockets, it's possible that we just live in one of those pockets. And maybe we were visited 1 billion years ago, and maybe there was a civilization that was set up for, 10,000 years, which is a lot longer than we've lasted. But all evidence of that is gone. The paper I did with Gavin Schmidt, the one on the Silurian hypothesis, where we showed that if there was a civilization here 100 million years ago, there's no way to know. There's no fossils. The only way you can find is to look for isotopic anomalies. So
sorry,
in that sense, I'm not so bothered.
I can't let you quite get away with that so quickly. I want to hear more about this. So how big of a civilization are you saying could have been here 100 million years ago? The size of our current civilization?
Easily. We're not going to leave. So
the equivalent of Manhattan would just be erased from the Earth in 100 million years.
It is ground down. Yeah. In that paper, as Gavin, pointed out, that the Earth's surface gets pretty well restructured, after a few million years. Certainly by 10 million years, anything that was on the surface is gone because a lot of the surface is gone, right? It's been subducted and come back up. So there's not a whole lot of there's almost no pristine surface from even, 100 million years ago. So with that, and then fossils, everyone's like, well, there'll be fossils. The fossil record is so incomplete. Very few things get fossilized. So if you had a civilization that was worldwide and that lasted 10,000 years, that is still so short that almost nothing you wouldn't find anything now, 100 million years later. So that's a pretty remarkable fact. That's why we wrote that paper, is just not that we were saying there was a civilization, but just like the interesting scientific question of could you tell? And the answer is probably not.
So two things come to mind immediately, but I can also come up with objections to them. One is that the chemical and atmospheric signatures would have been pretty enormous. And the other thing is, wouldn't have had a big effect on, not by leaving fossils, but by affecting other life forms, effects on the biosphere that would show up in the fossil record.
Yeah, well, the first one, the atmospheric record. It's really where you're going to have to look for for it. And this is what we did in the paper. It was in, I can never pronounce this, stratigraphy, in the strata. You're going to look for isotopic anomalies because the temperature went up or the temperature went down or plastics and as we showed, 10,000 years is probably too short to really pick out that. There are signals. There are definitely signals of interesting things happening, but they're very long, stretched across long times. And you can find better explanations like, climate change or, massive volcanic eruptions. But also, as we pointed out in the paper, no one's ever actually done the kind of high resolution studies, I just can't pronounce stratigraphy, that of the kind that you need. So that, in that sense, that's where you're right. That's where you'd have to look. Up to now, with what we have, you can't say there's anything. But we ended the paper like, hey, maybe people should look at this more carefully. And your second point, I forgot, what was your second point?
Causing mass extinctions or new fauna to show up or something like that?
Yeah, that's an interesting point. We did not consider that in the paper. My guess would be, but it's only a guess, is that, unless you lived for a very long time, you probably wouldn't be able to catch that level of something so short. I'm not sure about that, though. I mean, we are right. People would say we're driving a mass extinction. Will our mass extinction really show up or not? I don't know. So that's a possibility, and we'd have to look to see if that were true.
Okay, good. Here's my other crazy possibility. So what if civilizations last a little bit longer than you assumed in your paper? And so, but they're rare. So it's not surprising that we don't have one here in the galaxy. We haven't been taken over. But 1% of the galaxies that we can see in the field have been taken over by advanced civilizations. Is there any way we would know that? And have we looked?
So that idea of galactic engineering comes from the idea of the Kardashev scale, which we can very quickly go over. So Kardashev, in this golden era of SETI, right after 1960, Kardashev was a Russian physicist astrophysicist who proposed that there were 3 levels of civilizations. It's a good way of characterizing them based on their energy use. Type 1 harvested all the energy falling on their planet. Type 2 harvested all the energy coming from their star, a la a Dyson sphere. And type 3 harvested all the energy of all the stars in their galaxy, maybe even moving the stars around to clump them together.
Sure.
So people have not really looked for this. And the reason why people have not really looked for this is that, again, there's never been any money for this, right? To do a search like this, you need telescope time and you need graduate students and there's been never any funding for this. So maybe here and there people have tried this or that, but never been a coherent study of this. And hopefully now that things are changing, there will be the ability, some funding to look for those kinds of really galactic engineering or even planetary engineering. Here's an interesting technosignature that Jill Tarter came up with. If you looked at a solar system and saw 3 planets or 4 planets that all had the exact same climate, that would be a really good indication that those worlds, at least some of those worlds, had been terraformed.
That's a good one. Yeah,
I thought that was a really clever one. So, this idea of solar system scale engineering or galactic engineering, that's a great place. Yeah, that's a really good place to look, which, once we have a true program in technosignatures, we can do that.
But I think that the data has already been collected for the galaxies. We have galaxy surveys with spectra. All it would take was one grad student to take this up as a project and scan through the data from, Sloan or something like that.
Well, you have to know you'd have to figure out what exactly are you looking for. I mean, because, it's this is always the dilemma. How do you determine what's a natural signal and what's not a natural signal? I mean, so what nobody has done right now is articulated what explicitly would be the signature of that kind of engineering. So with the Dyson sphere, we say you need infrared. You need to have very bright infrared sources. And there's been a couple of studies of those, but not much. So, the first job is to figure out what the techno or biosignature is and then go look for it. You're not going to get telescope time or even archival time, right, to go look through all this unless you know what you're looking for.
Yeah, no, I do not agree. I think this is a very doable project. You got 1 million galaxy spectra. You ask a machine learning model to say, is there some fraction of these that look weird in a universally common way? And then you go back and look at those galaxies and ask if there's anything weird looking about them.
Well, you could do that. I mean, I'm wondering, I'm not sure if anybody has done, I mean, certainly people have done various kinds of anomaly searches for other kinds of things. Like, for example, the moon. We have enough data about the moon to look for any kind of, somebody left something from 1 billion years ago. But again, like, so people have done have done test projects with that. Like you can give like 50 square miles around the lunar lander and machine learning will find it immediately. Be like, that's different. But I still think with the galaxies, I mean, this would be an interesting question to look at. You still got to figure out, just finding, you can find weird things. And so you'd have a big giant box of weird things. But, sorting out the weird from the alien weird is, I think you're going to have to know what you're looking for. So I'd be interested to see if anybody's tried. I'm sure people have done this just for looking for quasars, right? Looking for odd quasars or such. But if you haven't created that category, is like, no, these are the things I want you to bin because they might be aliens. I don't know if anybody's ever done that.
Well, I guess that's what I'm getting at is that what for all the things that AI and machine learning are overhyped about, I think one of the things that they're pretty good at is, not making presumptions that humans make. So if you just asked it, like, is there a systematic way that some fraction of galaxies are weird? I'm not saying it's alien. Like maybe you make some other epochal astrophysical discovery, right? But just ask it that, and then if it says yes, these 3% of galaxies are really weird, then go back and look at them, and then rather than presuming what the signature would be.
Yeah. I'd have to say, I mean, it feels like somebody, for reasons that have nothing to do with aliens, people must have done that, right?
Exactly,
I mean, you saw that, it's interesting, when we, Tabby's star or Bergelian star, that star that people thought maybe we'd found a Dyson swarm around, was sort of exactly that. There was a pipeline from the Kepler data that was, identified transits automatically. And then it would spit out the ones that were like, I don't know what this is. This one doesn't make any sense to me.
Right.
And then there was a citizen science project that actually identified Bajoyan stars being like, wow, these don't look anything like a planet. And that is where, there were many possibilities. Alien megastructures was at the bottom of the list. But for a while, people were like, whoa, this is the kind of thing we'd expect if it was alien. So that was an example of doing exactly what you think. There's a machine learning algorithm for these transits, and then it spits out the ones that like, this doesn't look like anything I understand. But one thing I want to emphasize is from my perspective, I'm not a huge fan when it comes to technosignatures of like the galactic engineering because that assumes a level of technology and a level of organization and a level of cosmic coherence to a civilization that I'm not sure is possible. Because if the speed of light is really a boundary, then, it may be very hard to have galactic civilizations, right? If it takes, unless you're very long-lived, right? Unless your species.
Be very long-lived. You should be. You're super technologically advanced. Why should you have not conquered death?
That's a whole other topic. Not sure about. I mean, right. This gets into is right. Sure, if they're machines, right? If they are, if they're fully silicon, right? And I talk about that in the book. That's how long is the biological era? How long till we are replaced by our robot masters? But I still, there's that running in that direction still makes less sense to me than let's just look at the planets, right? Planets, let's just eavesdrop on the planets that we can have, because we couldn't do that before, right? And we could just look at these planets and look to see whether, again, anomalies, whether there's anything happening on the planets that is weird. And we couldn't do that before. So looking at that scale of galactic engineering, which is we just don't know. Whereas we at least have one example of a species of, life forming on a planet, that species becoming intelligent and changing the planet. At least, we have the existence proof for that one. So and we couldn't do that before. And so that's what I'm most excited about.
So what are we doing to look for life elsewhere? I mean, obviously, we're probably doing something very different to look for intelligent life than to look for microbial life. But we have this image of Jodie Foster sitting at a radio telescope wearing earphones. Probably we have other techniques rather than that by now.
That's the main emphasis for me that I'm trying to get people to understand is that is what I call classic SETI. And it's, great idea. But we've moved, that now becomes just a subset of this much larger array of possibilities, which was just never possible before. One of the things about the classic SETI that Frank Drake did is you kind of needed a beacon. You needed somebody sending a message at you focusing their radio energy. Because if not, if you were doing it, into the all sky, you'd need something that was so bright it was a star, right? So that assumed there was this whole sort of assumption that they want to contact you, they're interested in contact. Whereas now what's possible with JWST, et cetera, is that I call them metabolic technosignatures. It's just the civilization or the biosphere just going about its business. We don't have to really care whether they're trying to contact us. They're just doing what they're doing. And we're like detectives on a stakeout with our, in our cars, with our cold cups of coffee and our crappy donuts. And we're just watching the planet or the stellar system. And we're just looking for them going about their business. And that wasn't possible before. And now it is. So when it comes to life, we can look for these biosignatures, things like oxygen or, the network properties of the chemicals that we talked about before. When it comes to technosignatures, we actually have the capacity. We just wrote a paper on this. We could find chlorofluorocarbons in a planet 40 at our level, Earth level of chlorofluorocarbons, which if people don't know, that's the chemical we banned because it was destroying the ozone.
Yeah.
But it's absolutely not natural. There's no way we know to produce CFCs naturally. And we showed in a paper that the James Webb Space Telescope, with a couple of assumptions and about a few hundred hours of observing time, could detect chlorofluorocarbons at our level, certainly at 5 or 10 times our level, in a planet that was 40 light years away. So we can detect atmospheric, either pollutants, I'm putting that in quotes, because you may put chlorofluorocarbons into your atmosphere on purpose. Mm-hmm. If you want to terraform Mars, CFCs are a great idea. They're very good greenhouse. There's been a paper that's shown you could detect city lights, artificial illumination. There was a paper that showed you could look for, if you were deploying solar panels on a large scale, there's an imprint in the reflected light, the reflectivity changes. We call that the ultraviolet edge. And that would be detectable, just like plants, actually, there's a red edge, the reflectance of Earth already, you can see it. All the plants, all the chlorophyll puts a reflectance edge in the red. So
sorry. Say what is it doing? They're absorbing red or they're reflecting red. What exactly is that?
It is a change in, because of what it's absorbing in more in the blue green. It adds a change in the reflectance of light at the red light. So you see it climb at the red.
Okay, more red. Gotcha.
Yeah, because you're absorbing the blue green. So that's already, we've shown that Earth has that. Somebody looking at Earth for the last 2 billion years could tell Earth was an inhabited planet, right? That's what's incredible. All these things are now possible. And that's really what the book is about. In the next 10, 20, 30 years, we're going to have data. I don't know what's going to say, but we're going to have data relevant to this rather than yelling at each other about our opinions, man, which is pretty much what the last 2,500 years have been.
Hey, it's also what podcasts do. I don't want you to be bad-mouthing, yelling at each other with our opinions. But so which of these are going on? Are these programs, or are they just like individual investigators proposing to NASA to collect some data?
No, it's all in. So NASA is funding astrobiology in a big way. And again, the decadal survey really shows, right? The decadal survey said, look, the next $12 billion telescope you build is going to be about life. It's going to be tuned to find life. And that is just the tip of the iceberg of showing that NASA is all in terms of its funding. There's a number of different programs that speak to habitability, to biosignatures, to exobiology. Our grant is in the exobiology program, but there's lots and lots of others that NASA is funding. Everything from developing more powerful methods of atmospheric characterization to studying the cycles or the evolution of atmospheres. That's another project I'm involved in. Mm-hmm. Many of the planets we're going to be looking at are going to be close to their stars, what are called M-dwarf planets. These are the planets we're going to look for are orbiting the most abundant type of star, which is not the sun. The sun is not the most abundant star. It's a redder, smaller mass star, and the habitable zone for those are very close to the star. And it's possible that you just, there's so much crap coming off the star because of solar flares that maybe the atmospheres don't last. Mm-hmm. So, you got no atmosphere, no habitability. So that's a whole program. So NASA, across a wide range of fronts, is funding astrobiology as one of its major programs now. It's one of their principal programs.
And there is this opposite thing we can try to do, which is to draw attention to ourselves, right? To beam signals out to the world or to send probes out there with record players on them. Are we still doing that? And is that a good idea?
I am not a fan of METI, of messaging extraterrestrial intelligence. I have watched too much science fiction.
Exactly.
To think that's a good... I just really... the main problem with it is that who gets to do it? The idea that some astronomer with access to a radio telescope beams a powerful signal, to some distant star system just seems like... Of course we should consider the possibility that's a bad idea, right? We may decide, okay, we're wrong, but you have to consider the possibility. And so I think there really needs to be some kind of international body that debates this, makes it a public debate, and so we can decide whether we want to do this.
Yeah, I'm also of the opinion that maybe they would help us, maybe they would hurt us. Let's see first if we can figure some stuff out for ourselves before we draw our attention to this vastly more powerful intergalactic force that may be for good or for evil. Okay, well, how optimistic are you about this? I mean, it's certainly possible that the solution of the Fermi Paradox is that life happens on one planet in 10 to the 100, and therefore it's just us. Do we have any way of competently estimating how likely we're going to succeed here?
The best we can do, I think, is the work. I'm going to quote my own work here, but Woody Sullivan and I, a bunch of years back, did this paper where we said, look, there's the Drake equation, right? The Drake equation, the time-honored equation, which allows you to plug in values that you've made up and try and answer how many civilizations there are in the galaxy. And Woody and I asked, look, we've got this exoplanet data. What can we use it for, right? It's got to tell us something about the question about civilization. And so what we were able to do is, it's always with science, it's the question you can answer, not the question you want to answer.
Oh, yeah.
And so what we were able to do was we were able to manipulate the Drake equation and answer this question. How bad does the per planet odds for forming a civilization have to be to make us the only ones in the universe, right? The only time it's ever happened in the observable universe. And that answer turns out to be 10 to the minus 22, right? Now you can say, well, what does that mean? We don't have, is 10 to the minus 22 big or is it small? And for this, then you look at the literature, right? Because people have been trying to theoretically calculate or estimate in one way or the other what the odds of what this per planet probability should be. And then that's where you break up into pessimists and optimists. I talk about that in the book, right? And so in general, the pessimists were 10 to the minus 15, right? And even the most pessimistic of all pessimists, which was this calculation that was done, and suddenly now my brain's going to go blank on the author, but where they said absolutely, and it was a really interesting calculation that they did, kind of based on the anthropic principle. But they said, look, if it's 10 to the minus 20, we get 10 to the minus 20 for the probability of forming a civilization per planet, and that's so small that there can never be any civilizations around. Our number was 10 to the minus 22, which would mean that there's 100 civilizations before us. I mean, even if we can't observe them, it means it's happened before. So the only thing I think that's useful about what we did is it showed, we called it the pessimism line. It showed the difference between really what you mean by pessimism. And 10 to the minus 22 is small enough because what it is means that there's been 10 to the 22 experiments, right? Every habitable zone planet is an experiment in life and civilizations. And in order for us to be the only ones, it means every one of those experiments failed. And I think then it sort of falls to the pessimist to say, well, what is it? It happened with us, but what happened? Why? What are the filters that keep it from happening anywhere else? So that's kind of that's what I would say where I'm at with that.
So I completely understand where the number 10 to the minus 21 or 10 to the minus 22 comes from. That's the reciprocal of the number of planets that might be habitable. So that's fine. But I have no idea of how people are estimating the probability that a planet forms life in the first place. Forget about intelligent life or civilizations. Where are we getting that from?
Well, some people do combinatorics. They say, okay, how long do you have to wait for a DNA to, form by bouncing around? Other people looked at the number of species that formed and their durations. I think that's what went into because he was actually asking about intelligence. Other people will use the kind of a Bayesian analysis of when did life appear on Earth, which is pretty quickly, right? So, with the planet's 4.5 billion years old, by 3.8 billion years, we've got the zircons. I love that, the little zircons, whatever that's such a great word, that indicate that there may have already been life on Earth. So people have various methods. And of course, you're absolutely right. If you're going to say it all seems like, magic and smoke and mirrors, it is. I mean, it's very hard to do this ab initio. But people have tried various ways. And so there is a literature. There is a literature of people trying very clearly to do this. And one of our points in this was that, like, even the most pessimistic of pessimists actually turns out to be an optimist based on the number we got.
That is very surprising to me. Like, no one has said maybe the probability is 10 to the minus 40 of life forming. We seem to know so little about it.
Yeah. There's only one, and that was the combinatorics argument. But people, the problem with that was it was shown very quickly that you don't need to assemble DNA from scratch.
No,
so that argument was sort of went by the wayside, and people,
But the fact that life started fairly early on Earth is essentially meaningless to me, because you have to conditionalize on the fact that life already exists. We already know that. So it's not telling me very much. So I'm not saying that the number is small. I'm just saying, is there any principled reason to estimate that number, big or small? I mean, how advanced are we in coming up with theories for how life formed?
Yeah, there I would say we're still, especially in terms of being able to get a number that you'd like, I think we don't have it yet. I mean, we've made enormous progress in understanding the evolution of life on Earth and the possible routes for abiogenesis. But still, you being able to use that to get, you'll see there's a huge literature on this of people arguing back and forth, but I don't think there's anything of the kind you want. And in some sense, that's why all of these estimations, we just got to go look, we just got to go look and find. And the beautiful thing is we find one other example of microbial life and all bets are off, right? Now
What is your personal feeling about right here in the solar system? Are you optimistic about finding something?
Yeah, I am. Just because, God, I was just looking at this yesterday for this project we're involved in on looking at the interaction between planetary interiors and their atmospheres. And the moons, all those moons out there are like, there's so much water. So we are seeing so many subsurface oceans on these moons. So the moons around the gas giants and the ice giants were just formed with lots and lots of water. And it turns out that they have significant oceans hiding beneath either layers of ice, like Europa has I think like a 10-mile or 6-mile thick layer of ice, which is sitting on top of a 60-mile deep ocean. There's more water on the moon of Europa, which is about the size of Earth's moon, than on Earth, all of Earth's oceans. And it is just one of a handful, on the order of 5-10 moons, all of which have significant subsurface oceans. So I think there's a lot of possibilities out there. And the next, if we manage to make it through everything we're going through right now, the future, there's a lot of interesting possibilities of what could be living, what might have started in those oceans.
Is Europa your favorite target?
Europa is my favorite target because it's so cool. But, I mean, that's probably just my bias because I'm old enough to remember when Europa was discovered to be an ocean moon.
Yeah.
But Enceladus, which is orbiting Saturn, is a really interesting one because there you're getting the geysers. You're getting the water sprayed out into space, and you can fly things through that water. That's how we discovered the water was brine. Very salty, very good for getting life started. So I love Europa because it's so cool, but I think probably is, once we start getting out into the outer solar system, we may find other ones that are better to search.
How much credence should we put on truly wacky forms of life? Like, I'm sure you've read Dragon's Egg by Robert Forward, where there was life on the surface of a neutron star, or The Black Cloud by Hoyle, where it was some giant molecular cloud. Like, how open-minded should we be about the forms life could take?
I'm not wild about those, especially, in doing this work, I've had to look at a lot of the evolutionary biology literature, and one problem with the black cloud is how did it evolve? Like, how did you get the processes of Darwinian evolution to work for these interstellar clouds? So I tend to think and it's maybe my bias, but I think it's much better, especially because we can now. We don't need to think about, new life on neutron stars. We have finally the possibility of going out and looking for the kind of life we understand, which is made out of molecular modules, right? Our understanding of life is that it is principally driven by molecular shenanigans. You need these modules that can build bigger things, that can then take on different purposes, and that can hold hold information, have these gorgeous information architectures associated. And I just think that right now, because we can do it, that's where we should be spending our time. That's more likely, and we finally can do it, and there's a rich literature, rich understanding of evolution in a very generic sense that we can apply.
Okay, but don't come to me when the giant interstellar cloud gets mad at us for not taking it seriously and
dissing it, yeah,
wreaks
Sorry.
its wrath. Okay. All right, good. So we've gone this long without seriously confronting the whole UFO mess. Every 6 months, there's a UFO report, and I go on the internet and say, yeah, it's not really UFO. It's not aliens. And I always get like, but there's going to be a report coming out in the next 6 months that will reveal everything, and you will be ashamed. And so far, it has not happened to me. I mean, I don't know what your experience here is.
Pretty much the same thing. I wanted in the book to cover UFOs. About a third of the book is about UFOs and UAPs, because I wanted people to understand how to separate the wheat from the chaff, right? So the history of UFOs is one of, people seeing things. I'll never tell somebody they didn't see something. I wasn't there, right? Mm-hmm. But science is about public knowledge, and science has very high standards of evidence for good reason. It's why the cell phone works. It's why your knee replacement surgery doesn't kill you. And so a claim that, that something is related to life somewhere else in the universe is a huge claim. And you're going to have to do a lot better than fuzzy photographs and personal stories, no matter how compelling those personal stories are. So as I always like to say, there is nothing right now that would link there's no evidence that would link any UFO, UAP to something beyond Earth technology. We should do the search. I am all for, had the NASA panel. I think, people are so interested in this. I think we should do a full, open, transparent search, and we'll see what happens. And also, I'm glad the pilots have been able to come through. I've talked at length with Ryan Graves, the pilot, for one of the Navy pilots. And what I like about him, he's like very agnostic. He's like, look, I saw this. It was behaving in ways that no jet, I've been around a lot of jets, that no jet ever, moved. But, I need you guys to tell me what it is. He's not saying it's aliens. And he recognizes the fact that just seeing something is not proof, right? You need, and I have a whole chapter where I go through like, what would you need? Okay, if you really wanted to do a scientific search, what would you need? You'd need to build your own instruments so you understand them. You need a rational search strategy, and then you need some way to harvest all this data and comb through it. So, as you said, the problem with UFOs and UAPs is that the history of it is full of conspiracy theories and hoaxes, where everybody's always telling us next year, where the data is going to be released. It never happens. And so people need to really understand. They need a healthy dose of skepticism. As I like to say, you should think about UFOs and the claims made about them as if you had just gotten to Times Square and some guy says, hey, man, I've got $100 Rolex. Do you want to buy it? Right? Is it really a Rolex? Probably not. But,
I've seen it with my own eyes. And what would you say about the idea that from the aliens' point of view, talk to us about the plausibility of extraterrestrial advanced civilizations coming to visit us and being susceptible to having fuzzy photographs of themselves taken or crashing in Nevada?
Yeah, well, this is the real problem with it. It's like, look, this is what I want people to understand who are interested in UFOs. Because listen, people who really are interested in UFOs, for whatever reason, I think, cool, look, I'm interested in aliens. I love aliens, right? But, if you don't want to just believe, if you want to know, then you've got to kind of think the science through, right? You don't want to, I can write a science fiction story. You can write a science fiction story. That's not what we're interested in. So the idea, let's first of all take the whole idea that you saw lights in the sky, right? Because apparently the aliens don't want to land on the White House lawn and be like, yo, we're here. So that means they're trying to hide. And therefore, they suck at it, Right? Because, like, what? You can't turn the lights off? Like, there's this, there's a cloaking device that just doesn't seem to work. Or they've got a bunch of, 13-year-olds flying these things who've stolen it from their parents. So there's just that sort of coherent part of the argument. It just doesn't make sense that they don't want to be revealed, but they keep showing themselves. And then there's the blurry photographs. Photography has gotten obviously a lot better since 1947 with that's the first real UFO sighting that catches on. And yet it's always blurry photographs. It's always blurry photographs. And remember the Chinese spy balloon, right?
Yeah.
There was a picture, I think it's a selfie that the pilot, one of the U-2 pilots is taking, and he's holding the camera over his head, and you can see his helmet, and then you see the Chinese spy balloon, and you can see the rivets on the solar panels below the payload. And it's like, come on, why aren't there thousands of pictures like this? So and then there's the crashes, obviously the crashes, like the thing's able to get through interstellar space, and it crashes, once it gets here, because it got hit by lightning. That was part of the story in Roswell. I mean, they're sending us their 1987 Dodge Omnis, right? So it's just, I don't want to make fun of, people, but I just think you have to sort of you have to ask for a coherent, consistent, scientifically integrated story. And these are the kind of things that tell you that this just doesn't make much sense.
I mean, that's a good line you're selling us, Adam, but it's exactly what an agent of the deep state would be telling us if they wanted to hide the truth. So I have to maintain my skepticism so far.
Somebody said that to me on Twitter one time, and I was like, well, if I am, where's the check from the deep state? Because, I got more Mets paraphernalia to buy. And then he said, hey, everybody, you can see this is why this guy isn't trustworthy. And I said, you know what? That's what my kids said when I hid their Halloween candy in 2002. This guy's not trustworthy.
But it does, maybe this is a good place to wrap up, because it takes us back to the beginning where you mentioned the almost tension between the science of this and the science fiction of it, right? It goes in both ways. There are enthusiasts who are very invested in the existence and discovery of alien life, whether it's microbes or civilizations. And then there's a reaction against that maybe makes it hard to take it seriously. How do we balance those two very natural human impulses?
Yeah, I think, the whole point, this is the beauty of science, right? Science teaches you how to change your mind, right? I'm open. I'm literally doing a calculation now with some friends where we're looking at how long would the lunar lander be visible? How long on the moon before this process called gardening, which is micrometeorites just eroding. That's how the regolith ended up being so fine powdery. Because, look, I'm willing to consider that somebody came through 1 billion years ago and, left their lunch pail or whatever, or a monolith, who knows? I'm willing to consider the possibility if the data for the UAPs, let's say we do a UAP study and we do see things making right-hand turns at Mach 500.
Right.
If the data is good, I'll be like, okay, here we go, right? So the beauty of science is it shows you how to change your mind with honor, right? And I think that's what separates. I've met a lot of people in the UFO community and UAP community, and there are those who totally have that. They're like, look, this is what I believe, or I'm interested in, I think it could be. But the data if the data shows me something different, that's where I'll go. And what I found is there's also people not like this. I was just on the Tamron Hall show, and the whole thing was about UFOs. And I would talk to some of the people before we went on. And some of them, I brought them, and they were like, yeah, look, if the data goes that way. And there was one person in particular, unnamed, who I said, well, listen, if we were able to show that those pictures you were showing are natural phenomena, what would you do? And they were like, oh, no, I know that they were able to, right? So it's like, okay, now it's a religion, right?
Right.
So the point about science fiction is important, though, because a lot of my ideas come from good science fiction. A lot of things I'm interested in to pursue. Kim Stanley Robinson, there's a couple ideas he had that drove me to research projects. So I think there's a very important interchange between science fiction and this field, particularly when it comes to civilizations. And it's that scientists are not the best at asking some of the questions you need to, especially about civilizations, right? We're not trained in sociology or anthropology, or there's a way in which you need our imaginations to be lifted out of the kind of way we think of things. Scientists think of things. And so I've always wanted to have like a conference where we ask some of the best science fiction writers, a bunch of scientists posed questions to them and have them tell us stories that are focused that we might be able to drive us. So I think there is a very important interchange between science fiction and this field and thinking about aliens. But the point is to not get lost, right? Is to understand when something is just a science fiction story, untethered to reality, and when, because of course with science, what we need constrained imagination, right? We have our imaginations, let our imaginations go, but it's got to be constrained by the laws of physics and biology and evolution, even if we're going to extrapolate them. So I think that's the balance we have to find.
Well, I completely agree with you that the little nudge to the imagination that science fiction can give us is wonderfully valuable, and we should cherish it. At the same time, I worry a little bit. I just had Zach and Kelly Wienersmith on the show talking about the challenges we would face if we wanted to colonize Mars or the moon or something like that. I'm thinking also of just how people think about the future of AI or interstellar travel, and there's this idea that science fiction authors do the best they can, but they're telling stories, and they can sometimes give us the wrong impression about how easy certain things are, right? I mean, no one predicted the internet very effectively. Like, they may have mentioned the possibility of computers and being connected, but no one, as far as I know, 100 years ago was correctly predicting what the world would look like now. So on the one hand, I want to caution against taking science fiction too seriously, but on the other hand, is there a way that scientists can loosen up a bit and put their brains to work in thinking more carefully about the future? Because I feel like we're in this dichotomy between either thinking in science fiction-y terms or like scientists saying, if I can't build an experiment that tests it in the next 5 years, then I'm not interested.
Yeah, that's a great question. I think there is that space. And I think that's one of the things that makes technosignatures, this field that I'm in, so interesting. And again, I want you to recognize, like, while biosignatures is a very well-established field in astrobiology, technosignatures is new. I think there's like our grant and one other. Because NASA is still a little bit hesitant, like, alien civilizations, is that really, But I think the really fascinating thing about technosignatures is this attempt to systematize futures, right? To use that constrained imagination to really loosen up, to have some tools at our disposal, but also loosen up. And that really requires discussions it's got to be interdisciplinary. Like,
sure.
With the really exciting thing about technosignatures in SETI, I don't really use the word SETI anymore because I think carries a different kind of connotation. But technosignatures is that you got to talk to biologists. You've got to talk to anthropologists. What is technology? How do we even define technology? One of the things, there was a document that was done called the Indigenous Critique of SETI. And it was a bunch of indigenous scholars looking at the history of SETI and saying, like, here's a bunch of stuff you guys haven't thought of, because SETI was a group of men, basically, all sort of coming from a similar background. And they were doing great work, but of course they were limited, right? If you're going to think about the wide possibility of civilizations, probably having just one kind of human being from one socioeconomic group is probably not the best thing. And so I really love, even though I didn't necessarily agree with everything in the indigenous critique, I found it really opened my mind, right? It allowed me to consider other things. And that's kind of what we have to do. It can't just be science. It's got to be scientists in dialogue with, or it can't be just physicists and astronomers alone. We've got to be in dialogue with other scientists and the humanities and see how we can constrain but still expand.
That's good. And so I should just stop it there because that was such an eloquent statement. But I have one more question for you. It's a softball. Don't worry. Because I don't want people to, we're talking about this pretty dispassionately, but I think you're making the case pretty effectively that this is a prospect. It might not happen within our lifetimes, but it could, that we could actually detect, for even forgetting about civilizations, we could detect life on another planet in a kind of somewhat realistic way. And you said, at the beginning that this would be a big deal. Let's just sit and marinate in how big a deal it would be. It would be a hugely big deal.
Yeah. And I think it would be a hugely big deal for two reasons. Let's take life, just like, dumb life, if we even found microbes. The amazing thing, look, we're both theoretical physicists, right? And, black holes are awesome, stars are awesome, comets are awesome, but life is weird, right? Life is a physical system that, goes beyond itself. It creates, it innovates, it does stuff that no other system that we know of can do. And as for right now, it seems like we're an accident. As far as we know, we're an accident. It's the only time it's happened in the entire universe, which would be really weird. So to find just one example that it's happened somewhere else would sort of blow the doors off that. And I think we'd recognize that this incredible creative capacity is something the universe does. It didn't just happen here once by mistake. It's part of the universe. This creative, ongoing, expansion of possibilities that is evolution is something that could be happening all over the universe. And then who knows how far it goes, right? Especially once you get to intelligence, or you don't even need to have the kind of intelligence we have, like the idea of liquid brains. Like who knows what life, how life engages with the rest of the physical world. So that's number one. We would become part of this community of life, and that would reorder, I think, everything about the way we think of ourselves in the universe. Part two is if we found a civilization, it would tell us something very important. We all know, well, not we all know, but the people who are paying attention, as far as I'm concerned, know that we face a lot of challenges. There's some existential challenges to human civilization. Not to human beings. I don't think we're ever going to go extinct, or not anytime soon. But this global civilization we all depend on, from climate change to nuclear war to possibly maybe AI, it's not clear we're going to be here in 200 years in this form. And so finding one other example of a technological civilization would show okay, somebody made it, right? It is possible to do this. Because right now, we don't know whether or not sustainable long-term civilizations are even a thing the universe does, right? Maybe there are no sustainable long-term civilizations. So finding one would show us okay, somebody made it, and that would be an existence proof, and I think it would give us hope. So to close this up, I will say, when people say, oh, but it's not going to be that, it's not going to matter that much. You're going to find life 40 light years away. Who cares? And I like to bring up the Copernican revolution, right? Because in 1400, all the smart people went to bed going oh, look, tomorrow the sun's going to rise over the horizon because the Earth's the center of the universe and the sun goes around the Earth. 200 years later, all the educated people were oh, look, the horizon, tomorrow morning, the horizon's going to roll down and the sun's going to appear to... And that simple, nothing changed, right? But that simple astronomical fact was implicated in the Renaissance, was implicated in the Enlightenment, was even implicated in the Protestant Reformation, right? It became a building block in this profound transformation in how human beings understood each other. And I think the discovery of life, no matter what kind it is, will be the Copernican revolution times 1,000. It'll just rewire how we understand ourselves.
That's a good science fiction plot. We discover the existence of intelligent life elsewhere. We don't even get to talk to it, but it changes our civilization here in a dramatic way.
Right. It leads to that, along with maybe other things that are happening to us, because we are facing, we have a problem with the biosphere. It's clear the biosphere is about to get rid of us, right? And so maybe the discovery of life elsewhere sort of we need this new understanding of our place on the planet, and maybe that would be part of it,
Sometimes shaking things up is a good thing. So Adam Frank, thanks for your contributions to doing exactly that. And thanks for being on the Mindscape podcast.
Thank you, Sean. This is really fun.